So this lecture is going to be on sinusoidal waves. So continuing where we left off, thinking about wave shapes. This is a particular shape that looks like a sine or a cosine function. The source of a sinusoidal wave is a source that vibrates with simple harmonic motion, like a mass on a spring. So it goes back and forth, up and down in a very regular, periodic way. Here's a little demonstration we saw previously. If we just click the little play button, you see the hand moving up and down, kind of like a mass on a spring going up and down, holding a piece of string. And the piece of string has a traveling wave on it, a sinusoidal traveling wave that looks like a sine or cosine function. This little red dot just identifies one point on the string, and that point goes up and down in simple harmonic motion, like a little mass on a spring. So this is a sinusoidal wave, one that looks like a sine or a cosine function. And the medium vibrates like masses on springs, like simple harmonic motion. When we look at this snapshot, if I pause this anytime, we can talk about how big the wave is, we can talk about its amplitude, we can also talk about the distance between the peaks, the maximum. So at this instant in time, the string is at a maximum displacement from equilibrium. Equilibrium would be right along this line here, where the string was when there was no wave. At this point here, the string has been displaced a maximum positive distance, and also over here. That distance is what we refer to as the wavelength, that distance between a maximum and a maximum. It's also the distance between a minimum and a minimum, roughly over here. These pictures down here show that a little bit more clearly. Here's a snapshot graph where we're taking up a picture of the wave at one instant in time. And here we're just assuming the wave is moving to the right, as we had up in this animation. So the distance between the peaks is the wavelength. It's just the name of that distance. That's what we call it. This Greek letter lambda is what we use to talk about wavelength. And we talk about the amplitude also as the maximum distance from equilibrium. So the string originally, without any wave, was along the x-axis, just flat. And with this sinusoidal wave on it, it goes up and down, above and below the equilibrium position. It goes up to some positive maximum value and down to some negative maximum value, the same value, same absolute value above and below equilibrium. We refer to that as the amplitude of the wave. We talk about a crest and a trough. A crest is a peak, a trough is like a dip in the wave. And then there's, of course, the wave speed that we talked about. V is the speed of the wave. If we think about, instead of looking at a snapshot graph, instead of taking a picture of that whole piece of string, for example, to see the shape of the wave at one moment in time, if instead we look at one piece of the string and look at how it moves as time goes on, we get, again, what we call the history graph. And again, this is at one point in space, like x equals 0, for example, but as time goes on, that one point goes up above equilibrium, comes back to equilibrium, goes down below equilibrium, comes back to equilibrium, goes back above, back below, back above, back below, and so on. So this horizontal axis is time, and we talk about the distance in time between maximums. We call that the period. So the period of a wave is, if you imagine being at one location in space, asking how long does it take for the medium to move from maximum displacement to, again, maximum displacement, or from minimum displacement to minimum displacement, or whatever 2 points are the same, from, say, this point to this point. That's the period of the wave. Another way to think about it is it's the amount of time that it takes for one complete wave cycle to move past you at one point in space. So that's the period. So we have period, wavelength, speed, and amplitude. And then finally, the vertical axis is labeled with D, and we'll talk about that in a second here, actually. So what's some relationships between period, wavelength, speed, and frequency? If we think about the amount of time for one period and what happens, as I said before, on the time of one period, each point in the medium vibrates through or cycles through one complete vibration. So every point in the medium goes from being at one displacement all the way around to some other displacement back to where it originally was. So this point right here, this little red dot, goes from being at a minimum to maximum to minimum. Maximum, minimum, maximum. Minimum, maximum, minimum, and so on. This little green dot that keeps flying by is just stuck on a maximum. So the speed of that green dot is the speed of the wave. And this red dot just represents one point in the medium vibrating up and down. And so as one wave passes by, once that green dot gets over here, as one wave passes by, this red dot goes through one complete cycle of motion. And so you can kind of see that if you look carefully. That green dot passes through one complete cycle, or the red dot, I mean, it's there at the top, and it's there at the top again. And there's one complete cycle of motion. Let's see if I can pause that right about there. Pretty close. So the red dot is back up at the top, almost back up, just a little bit beyond being back up at the top, and the green dot is just about one wavelength away from it. Right? So the total time that it takes for a piece of the medium to make one complete cycle of motion is the same as the time it takes for one wavelength of the wave to pass by. So if we think about the speed of the wave, the time it takes for the wave to pass one point in space, that distance traveled is one wavelength. And the time that it takes to travel that distance is what we call the period. So the distance the wave travels during one period is lambda, the wavelength, and the speed, the time itself that this happens over is called the period. That distance divided by that amount of time is your speed, meters per second or centimeters per second, whatever that might be. So here's an equation that we can use to describe the speed of the wave. It's a wavelength divided by the period. If we think about the period is time. It's the number of seconds, or we can think about it as seconds per cycle. Seconds per cycle. How many seconds does it take for one complete cycle of the wave to pass by? If we think about the reciprocal of that, if we think about 1 over the period, that would have units that are the same as the reciprocal of cycles, or seconds per cycle. In other words, it would be cycles per second. So this is something we call the frequency. It has units of cycles per second rather than seconds per cycle. And it's often referred to as the hertz, cycles per second. So frequency is 1 over period. And then if we combine these equations, and this velocity equation is lambda divided by period, that's the same as lambda times frequency. So this equation here is another way of writing the speed of a wave. And this would really be technically, the speed of any kind of a wave that repeats itself over and over and over again. Not necessarily just a sinusoidal wave, but any wave that has a definite repetition to it. So, any wave that repeats over and over and over again has a wavelength, that has a distance in space over which it repeats. And it also has a time. It has a time in space over which it repeats. And those two things combined, wavelength divided by time, is the speed. The problem, though, is that this equation is technically only valid for periodic waves, and periodic waves are technically things that happen, over and over and over and over and over again. So technically they are waves that exist throughout all of space because they keep happening over and over and over again. And in reality, those really technically don't exist. But most waves are very good approximations to these perfectly periodic waves. So we're often using these equations anyway. It doesn't really hurt us too much. It's not something we're going to worry about in this class, at least. So this is pretty much the equation we're going to use. So let's think about how you represent these things mathematically. Again, I refer to this letter D we're going to use. We're going to try to represent things not thinking specifically about transverse or longitudinal, but both of them at the same time. Either way, there's some displacement of the medium, whether it's a transverse wave or a longitudinal wave. The medium is getting pushed around. And so we just call that capital D. If this is a transverse wave, then this capital D really represents like a delta X, or a delta Y, I guess. If the wave is moving in the X-axis, along the X-axis, and is a transverse wave, then the medium is moving along the Y-axis. So this displacement D would really represent like a delta Y, something in the Y direction. If it's a longitudinal wave, then the displacement would represent like a delta X if the wave is moving in the X direction. So big D represents different things. So the equations we're going to talk about here are valid for whether we're talking about transverse or longitudinal waves. So the sinusoidal wave has a shape of a sine or a cosine. So obviously in our mathematical representation, we're going to use a sine or a cosine. It's going to depend on time because, of course, it moves. The shape moves as time goes on. So time is going to be in the equation eventually. And it certainly depends on position because at different positions at any given time, the wave has there is a certain displacement. So what we're going to do is we're going to think about time equals 0. Just for now, just imagine that time is 0. We're just kind of starting our stopwatches. We haven't quite started them yet. We're just calling that moment in time 0. Now let's just think about a sine function that is a function of x. And the sine function has a certain amplitude. The medium gets displaced from some positive a to some negative a. And the shape of that displacement is a sine function of x. And I put a little question mark in here because x has to be in here. It's a sine function that depends on position. But can I just put x in here without anything else? And the answer is no, because x represents a distance, meters, centimeters, whatever it might be. And the thing that you put inside of a sine function is an angle. Technically, it has to be in radians. So really, this thing in parentheses is unitless. It doesn't have units. So what we want to do is think about having to have some kind of a factor in here that kind of converts meters or centimeters or whatever it might be into radians. So if you think about this question mark as being like a unit conversion factor, converting meters into radians, how do we do that? Well, if we think about the wavelength lambda, we can think that we can understand, or we can kind of remember that if we have one wavelength of a sine function, one wavelength of a sine wave, that over that distance is when the sine function repeats itself. You get one wavelength that goes through one complete cycle, the next wavelength goes through another identical complete cycle. So in one wavelength worth of distance, this angle within the sine function has gone through 2 pi radians, has gone through one complete circle. If you think about back to like the unit circle kind of idea, as the angle goes through 2 pi radians, the argument of the sine function or the cosine function, that function repeats itself. And so we can think about the distance of wavelength as being sort of an equivalent kind of thing as 2 pi radians. They're not equal because they're different things altogether. But what we can kind of say in a sort of crude mathematical way is we can say that 2 pi radians equals 1 lambda. I mean, technically this isn't right, but that's why I put this in quotes. It's not quite right. You know, it's not really a exact equals. It's sort of like they're sort of equivalent to one another. But if I think about taking this and thinking about this as a conversion between wavelength and between distance and radians, 2 pi radians is 1 lambda of distance. We can kind of use that as a conversion factor to convert this x that has units of distance into some big quantity that has units of radians. So we have 2 pi divided by lambda here because that's what we're using to convert. There's 2 pi radians in one wavelength of distance. Multiplied by the amount of distance we have would give us the total number of radians that we have. And that's then our argument for the sine function. So here's a little plot of that. I can change wavelength here. Right now I've got wavelength set to 0.5. And here's my wave, and there's a lot of cycles in this wave. It goes up and down a lot of times, up and down from minus a to plus a. And each little tick mark here is labeled with a lambda. Lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, etc. And you can see how, as I change the wavelength, the wave gets longer, bigger. And it's just a sine function, so it always starts at the origin, like any sine function does. But as I increase the wavelength, the thing gets more spread out. The wavelength gets bigger, the peaks get further apart. And I can make these really big. So there's 1 wavelength, 2 wavelengths, and so on. So, what about cosine? We chose sine. What about cosine? Do we just ignore it? If I was cosine, I'd be kind of sad about this. But what we do is we say, if all we're going to do is use a sine function, if that's all we ever do is use a sine function, then what that means is that at x equals 0, the displacement of the medium is always 0, because a sine function is always going to be 0 when x is equal to 0. And that isn't necessarily always going to be right? You set up a coordinate system however you want to set it up, and you have your medium with your coordinate system, and it's not always going to be true that at whatever point you're calling x equals 0, that the medium is never displaced there. That doesn't make much sense. Or at least at time equals 0, it's not displaced. Again, this is a traveling wave eventually, so we do have to add time to this equation. And so technically, as time goes on, this wave will be moving maybe to the right or to the left. And that point at x equals 0 will eventually get displaced. But it's not necessarily always going to be true that when time is equal to 0, that point that you're calling x equals 0 is going to have 0 displacement. So what we do is we add something to the sine function. We add something inside the argument of the sine function called a phase constant. So we rewrite our equation to look like this. d of x, and I have d of x come as 0 here. I should have pointed this out before. That 0 is time equals 0. This displacement function is going to be generally a function of x and t, but for now we're just going to let t equal 0, so time is not going to show up over here. But now I'm adding this phase constant into the equation, an extra angle that I can add to this angle over here. And what that allows you to do is it allows you to set up whatever situation you want at time equals 0, and so that the medium at x equals 0 is not necessarily at equilibrium when t is equal to 0. So let's see how that works. In this little animation, here's the sine function. The amplitude is a, and I got minus a there. I right now have a wavelength of 2.5 meters, and I have a phase constant of 0. And so when you have a phase constant of 0, this thing is just your plain old sine function, something times x. And so it oscillates up and down, lambda, 2 lambda, 3 lambda, and with a phase constant of 0. Let me just click over and just see what happens here if I make it a pi over 6 phase constant. This is t equals 0, so this pi over 6 phase constant has shifted the sine function. The sine function has been shifted to the left a little bit, so that at x equals 0, the displacement is now some positive value. The displacement is now some positive value, it's not 0. So this is still time equals 0 for this wave, and the displacement is not 0. But this isn't a cosine function anymore. It's not a pure sine function anymore. It's a sine function with an extra little angular piece in there that doesn't depend on position. If I change this a little bit, again, pi over 3, this is again at t equals 0, and the displacement of the medium at x equals 0 is some big value now. It's significantly displaced from equilibrium. And if I go to pi over 2, now I've got a cosine function. So a cosine function is the same as a sine function with a pi over 2, and that's been cut off a little bit there, with a pi over 2 phase constant in there. I can put negative values of the phase constant in here, negative pi over 6, and that shifts the sine function in the other direction, to the right. And so other phase constants shift in greater distances. And so we can pretty much do anything we want. I've only selected, a few different phase constants to put in this little simulation here. But you can adjust these, you can adjust the phase constant to be any number you want it to be, so that at t equals 0, the medium is displaced in one particular displacement. You can select what that value is, and you can figure out what that phase constant has to be to have the medium at x equals 0, have that specific displacement. So that's what I said down here. The phase constant phi 0 is determined by knowing what the medium's displacement is at the location x equals 0 and at the time t equals 0. So in other words, if you look at this equation down here, if I plug in x equals 0 into my displacement equation, I of course have a sine of 2 pi over lambda times x, but x is 0, plus phi 0. Well, this whole term is 0 here, so I just get a times sine of phi 0. So in other words, this is saying if you know what the displacement is at x equals 0 and t equals 0, if you're given that information, then you can solve for what that phase constant has to be. Or you can go the other way. If you know what the amplitude is and you know what the phase constant is, then you can figure out what the displacement of the medium is at your position of x equals 0 and at a time of t equals 0. So if we think about an example here, it's just it's written out here. If at t equals 0, a sinusoidal wave on a string causes the piece of string positioned at x equals 0 to have a displacement of minus 0.5 a, where a is the amplitude, then we can write this. So we're saying that a is the amplitude. It could be 5 meters, it could be 10 meters, it could be 2 centimeters, whatever it is. It just so happens that at time equals 0, the point at x equals 0 has a displacement of negative half of the amplitude, meaning that that point is somewhere down below equilibrium, negative meaning below equilibrium, and it's a half of the amplitude below. It's like halfway between the equilibrium and the maximum negative displacement. So what that means is that negative 0.5a is this displacement at x equals 0 and t equals 0. So negative 0.5a is this d00 thing. But d00 is always a sine of phi 0. It's always that. So we set these things equal and we get this equation here. So we can solve for phi 0, then the a's cancel out, and we have that negative 0.5 is equal to sine of this angle. Well, now we all memorized trig functions, I'm sure, right? Everybody knows all their sine and cosine functions. I mean, angles, sine of pi over 7, everybody knows that, of course, right? Well, maybe not. So we can use Mathematica to figure it out, and you could use like the arcsine function to figure out, or sine inverse function, whatever you want to use to figure out what is the sine inverse of negative 0.5. If you do this in your calculator, you might get just one number. You might get one angle of like negative pi over 6 is one possibility. This angle of negative pi over 6, sine of that would give you negative 1/2, just like what we want. But there's usually, pretty much always going to be two angles that'll do this for you. Maybe not always, but most of the time there'll be two angles that'll do this for you. And in this case, there's also another one, negative 5 pi over 6. That also gives you a minus 1/2 when you took the sine of that. All right. So these negative angles are angles. Remember that the standard angle goes sort of counterclockwise. The positive goes up counterclockwise away from the x-axis, and the negative angles kind of go down clockwise from the x-axis. So this is an angle. This is like pi over 6 degrees below the x-axis going clockwise. This is 5 pi over 6 below the x-axis going clockwise. The positive angles would be counterclockwise. So we have two angles here, minus pi over 6 and minus 5 pi over 6 that satisfy this relationship right here, this equation. So which do we use? And actually, it's worse than that. There's really an infinite number of angles, because you know that you could take any angle that you plug into a sine function. You could add 2 pi to it, get a new angle, plug that into the sine function, and you get the same answer. Because these sine functions are periodic. They repeat over and over and over again. So really there's an infinite number of angles. But what we do is we restrict these phase constant angles to be whatever angle is required between minus pi and plus pi. And that covers a full circle worth of angles. And that's all you need. You don't need to go beyond a full circle worth of angles, because otherwise you just get repetition in your trig functions. The question though is which of these angles do we use? So which of the angles? Minus pi over 6 or minus 5 pi over 6? And the answer depends on the speed of the wave and what direction it's moving, actually. It depends on which direction that piece of medium is going. So what we're saying is that, we have a situation where the wave is causing this point at x equals 0 to be below the equilibrium at minus 0.5a. But we're not told, is that point in the process of moving up, back up to equilibrium, or is it still moving down, away from equilibrium? We don't know that. We're not given that information. So that has to do with the speed of the wave and the speed of the medium as the wave is moving past. So we can't answer that question unless we think more about the speed of the medium, the speed of the wave as it moves, and things like that. So we have to add time to this picture. We have to talk about how do we incorporate time into this equation, and think about the fact that this displacement equation gives you displacement of the medium, but all we're talking about so far is a displacement at a particular time. To understand something about the velocity of the medium, whether that point is moving up or down, we need the velocity of the medium, which requires a derivative of the displacement. So velocity is the derivative of the displacement. This is the velocity of the medium, not the velocity of the wave. So we need to incorporate time into this equation. We can't just have time equals 0. And we can take a derivative of that, and that'll give us the velocity of the medium. And by knowing what the velocity is doing at time equals 0 and x equals 0, then we can choose whether whether we're going to use minus pi over 6 or minus 5 pi over 6. But there's another way that we can kind of do it graphically. If we look down here, let's put in the minus pi over 6 phase constant. So let's just click here. Oops, there we go. So here's a phase constant of minus pi over 6. So here's my x equals 0 position, and it's at a negative 1/2, negative 1/2a displacement. Well, the question is what is that piece of medium going to do as time goes on? This is at time equals 0, but what's going to happen in a half a second? What's that point going to do? Is it going to move back up to equilibrium, or is it going to move back down to the maximum negative displacement? Well, the answer depends on which way the wave is moving. So if we know the wave is moving to the right, all these ripples are going to move to the right as time goes on. And what that means is that this minimum right here is eventually going to get to x equals 0. And that means that this x equals 0 point that's right here is going to eventually move down there. So if we know the wave is moving to the right, and we choose a phase constant of negative pi over 6, that means that this point in the medium is still moving downward. because this negative part of the wave is still approaching. It hasn't gotten there yet. Okay. If we choose if the wave is moving to the left, let's say, and we have this negative phase constant, then this part of the wave, this maximum, is going this way. This minimum has already been here. And so this point on the string has already been at the lowest displacement. It is moving back up toward equilibrium as this wave moves to the left. So choosing the correct phase constant not only depends on satisfying the displacement equation at time equals 0 and position equals 0, but you also need to know, which way is the wave moving, and look at a graph like this, or you need to find the equation for the displacement as a function of time, which we'll do next, and then take a derivative of that to get the velocity of the medium, and look at what that is. Is it positive or is it negative? So if the medium is moving downward at this moment, the velocity would be negative. If the medium is moving upward at this moment, the velocity would be positive. And so from that you'd be able to tell what direction the medium is moving and which phase constant would give you the correct direction. So we need a little bit more information. We haven't been told in this example whether the wave is moving to the left or to the right, or whether the point in the medium is moving up or is it still moving down. We haven't been told that. So the best we can do at this point is just say that there are two angles that satisfy this, minus pi over 6 and minus 5 pi over 6, and that's all we can do right now. We need more information about the velocity of the wave or the velocity of the medium itself to figure out the rest of this. So the next lecture is going to be trying to do this. We're going to try to talk about traveling waves, and that is taking these snapshot graphs and adding time to them to make an equation that represents a wave that's actually traveling. And then from that we can get information about the velocity of the wave, but also the velocity of the medium itself, and that's a different thing than the velocity of the wave. So look for the next lecture, lecture 3, on traveling waves, and we'll come back to this displacement equation for the wave on a string, the sinusoidal wave. So right now this is what we have, and we'll come back to this and add time to this and see how that works, and then we'll talk more in detail about these phase constants and how to solve for them. So until next time, have a good afternoon or evening, whatever it might be, and feel free to email me anytime you want with questions, jcarzoli@oakton.edu. Take care.